So I will use this stream to recap and make some review of the different PCB design I've done so far. So okay, so if we sum up what this project is about, it's called CleverHand. It is a modular and wearable high-density EMG acquisition system. So let's talk a bit more about this. So maybe I can make a small introduction of what EMG is. EMG is the signal that are created by your nervous system when trying to control your muscles. So your brain sends some electrical information, and this electrical information can be detected just on your skin or inside your muscles. So it's very interesting to be able to record those signals for medical purposes, but also for example, study purposes. So for research, it might be very useful to know how the brain is controlling the muscles. So it's not a new technique, and it has been done for a long time. You have some very cheap and affordable sensors that are available on the market. For example, this SparkFun, you can buy it on SparkFun. It's just a one-channel EMG acquisition system. I think it's around $40. You used to have the myoband that is not available anymore, but that was able to provide 8 EMG signal. So it was quite practical for research, because you just had to put the bracelet and you were able to record muscle activity from the arm or the biceps or different muscles like this. More recently, you have Meta, that Control Lab from Meta, that have developed a new myoband 16 channel, but it's not, I think, publicly available yet, and we don't know so much about this. And you have a very high density devices that are able to record a lot of channel, a lot of different points on your skin. They are able to measure the electrical activity on your skin or inside your muscle, and you have a lot of signal. So the more signal you have, the more precise you can be on the decoding or on the control that you want to make with your device. However, they are very not wearable and not very portable. So, and they are very expensive. So I wanted to work on something that was able to make a mix. So having high density while still being wearable and affordable. So I've designed this type of electrodes that are wearable. So everything is described on my GitHub, but it's a wearable device that is very modular. So you can plug the module one after another. So you can have just, for example, 8 electrodes or up to 16 modules, so 16 times 8 electrodes with different features that are able to record at 2 kilohertz with quite a good resolution and in bipolar and monopolar mode. So I've done a lot of different try and error, but this is the current structure of the device. So I am plugging the different module together like this, one after another. I'm chaining the module, and I'm communicating on the SPI bus that is able to reach quite a high sampling frequency rate, communication rate. And obviously, so right now I'm recording up to 16 module, actually now up to 32 module, but if you need more, you can link and synchronize the different masters together. Right now I'm recording EMG, but I've also developed other modules that will be able to provide some inertial measurement to know how the muscle are moving, or to provide feedback, so for example electrical feedback or vibratory feedback. Here are different prototypes, different version of my project, but I've done some more. So yeah, so this is the introduction, and you can find I will copy this link. So this is a GitHub. You can find all the information about this project. I'll copy paste it in the chat. Yep. So this was the previous version, but during those 3 last streams, I have designed some new model that I will describe right now. But on this GitHub repository, you can find different information on the current available product that are able to record EMG, their price, their capabilities, and what I'm trying to do. So yes, this is the description of the structure. So it's quite it's still quite complex, but the idea is that I really wanted to make it very modular. So you can plug together communication module, and on each communication module you can plug EMG or IMU or different sensor or actuator module that you can themselves connect to different type of output form factor that I will describe right now. So if we hide everything, okay. So for example, here in this diagram, the communication module needs to be connected to other communication module via FPC, so flexible connector, the one that you can find in the computers. So what you do is you connect the input inside this one, for example, and then the output inside this one, and so you can chain together different communication module. The communication module should be able to process or manage which one is being addressed. So the master, the microcontroller, is sending information on the shared bus. However, the master is sending also an address to select which module the master needs to get information from. So the master will first, for example, address the first one, then communicate, then it will address the next one, then communicate, etc. So this way you can have as many modules as you want, and get information from each of them independently. Here on this module you have different parts. You have a microcontroller, an ARM microcontroller, that is at the initialization giving individual addresses to each module, each communication module. And you have this bigger chip that is identity comparator, that is actually comparing the address fixed at the beginning by the ARM with the one that is sent by the microcontroller, and it's doing it in real time at a very, very fast pace. So it's able in 14 nanoseconds to evaluate if the address sent by the microcontroller is the same as this module address, to know if it should be activated or not. And on the other side you have 2 LED that are controlled by the microcontroller. So it's very practical and useful to have some feedback on each module, so it's easier for the user to know, for example, which module is communicating with the microcontroller, or if you want to send some information. For example, if you have a lot of modules and you want to know which one are recording the most EMG or the most intense signal, then you can program the microcontroller to create some visual feedback with the LEDs. I also put a button, but that will not be the correct one. It will be one that will be closer to the side of the board. So this is the communication module. And on this communication module, you will connect different sensor modules. So for example, in my case, it will be EMG module. So the EMG module will be this one. Up. If I hide the communication module, up. So this EMG module is communicating with the communication module via these connections, and it is here. It provides you some electrodes or some input access to record EMG. So this one is specialized in recording EMG. It has here a small voltage regulator to help it to help having a very smooth power supply, and you will be able after to connect different pins, different connector to those castellated hole and record EMG from there. If we watch sorry, I forgot just before to show for the communication module, the schematic is as follow. So you have the two connector that I was describing. You have the comparator that is comparing the address of the bus of the microcontroller to the one that is provided, to the address of the bus to the one that is provided by the microcontroller at the beginning. You have the two LED RGB LEDs, and you have some additional external port and the communication port that is connected to the EMG or the sensor modules. Okay, so this is for the communication. For the ADS, so for the EMG that I just described, the schematic is even simpler. So you have this chip that is specialized in EMG acquisition that will be connected to the castellated hole here. So this one has up to 6 input. What I did is I connect, since I want to be able to reach up to 8 input on my connection. Here they are connected together, and you can reroute them by software inside. It has 3 simultaneous ADC, so analog to digital converter. So the idea is that the signals that you get here is electrical signal from the muscle that you need to transform into a numeric into a digital information that you will send to the microcontroller and then to the computer. And yep, and you have the crystal that is required to make this one run. However, it is huge compared to the rest. If you look at it, it is taking most of the space of the board. But the issue is that with this frequency, so it is 4 megahertz, yeah, 4.096 megahertz. You don't have smaller form factor, so it's very sad. However, it should be fine with this with the setup I used. So yeah, you have the connection module that is linked to this, the communication module that is linked to this sensor module, so this EMG module. So now what is left is something to connect those castellated hole, to be able to connect them to the skin, for example. So the simplest and most direct way would be with dry electrode like this. So if we hide everything, up, you have the 8th connector from the EMG board that are connected here, and that will be linked to each of these pads. And so now if you put this on your skin, on your arm, or anywhere on your body, on your shoulder, you could even put it on your face, you will be able to read electrical signal from each of these gold-plated electrodes. So that's the idea. Also, yes, in terms of size, I didn't precise, it is very small. If you see here, oops, it is for this one around 20. Ooh, it's not at the right scale. 21 centimeters, huge. No, it is. We can see in this one. Boom, boom, boom. Here. So, for example, for the EMG, you will have something that is 15 millimeter by 11 millimeter. So, if we go back here and we put this one is 15 millimeter in width and around 11 millimeter in height. So quite small, and you can put a lot of them together. Let me remove this. Oops. Not how to remove. Okay. Okay, so now you have these 3 modules. If you connect them together, you have a working module, let's say, that is able to record and transmit EMG signal to a microcontroller. So next stream, I will receive those boards, send them to GLC PCB to have to manufacture them. Since it is just a prototype of this version, I asked them very simple without too much. For example, I think I didn't select gold plated. The castellated hole will not be might not be properly done. So yeah, I chose the cheapest features. However, we will be able to try and see if it's working. If it's working correctly, then I will be able to order a bigger batch with better quality. Okay, so this is the simplest module, but obviously you can add different things. So for example, if you want to use, if you don't want to use dry connection directly, if you don't want to put this directly to your skin, what you can do is connect this board to another one, to this one, and this one will connect each pad to jack connector and use more traditional wet electrodes that you will stick on your arm or on your muscle. This way it makes this module very easy to use in different situations depending on your need. So this is one possibility. So the possibility is to use a dry electrode again, but a flexible one. So this one is very, let's say, experimental in the sense that I really don't know if it's going to work, but let's see. So the idea is that each of these, it will be printed on a flexible PCB, and each of them will be curved below and then soldered back here. And so this way you have some kind of elasticity on each pad, and we will see if it helps or not. And another thing is you can add other module on top. For example, this one that will be directly communicating with the ARM microcontroller that is here. And so this way you can add more features to each module. And for example, this one, it's IMU, it's a BNO 055 that is able to measure inertial information. So for example, orientation in space or acceleration. And so this way you can you know the motion of each module and it can be very interesting to get some fusion from this and from the EMG data. I think that's all for the different module I've designed and ordered yesterday. So we will see what happened, and we will see how it comes. So next stream I will probably do an unboxing from these different PCBs and try to do some soldering. Oh yeah, so to save some money, I just ordered the stencil of each of them, and so I will have to solder by hand each of them. So it's very small parts, so might be interesting and challenging to try. And yeah, so everything will be summed up on my GitHub, and you will have access to the different schematics of the different modules. They are quite simple for most of them. It will be more tricky to assemble them, but let's see. Also, I didn't order yet, but the idea is that, for example, in this case, I am recording with ADS 1293. However, there are more advanced models like the ADS 1298 that is able to record from 8 input. So the idea will be that this module can be replaced by another module that has the ADS 98, and you will be able to connect it to the communication module indifferently and get access to more channel and have more EMG signal recorded simultaneously. Yeah, I think that's it. I might also do a stream to talk about the programming part, so how to interface the communication. So I will have to program each microcontroller, so there will be a firmware stream. There will be a driver stream to how to interface each board with a computer by writing a driver in C or C++ probably. And another one, oh yes, I think I have a description. So here there will be a firmware in each ARM microcontroller, but you will also have the driver in the computer that will have to interact with the microcontroller. So right now it can be used with any microcontroller. So I might at some point make a more dedicated microcontroller form factor for this project. However, for now I will just use a Teensy. So with a Teensy or a Raspberry Pi Pico. So right now it should be able to communicate via USB, Ethernet, or USB, or Wi-Fi. So via USB, just because it's simpler at first. You just have to plug it on your USB port and you can read all the information. Via Ethernet is if you want to reach faster sampling rate, and with Wi-Fi is if you want to be more portable and wearable. You don't want some wires to be in between the user and the computer, so you can communicate via Wi-Fi. In any case, you need the PC to be able to understand this information. So I will do a stream describing the driver I wrote and maybe some improvement. And you will have another one that will talk about the Python API I've written that is able to communicate with this driver to let you have access to different functions that lets you, for example, open a connection with a chain of module, that let you set up the different parameters that you want, that lets you read information from the EMG or from the different other sensors. I've also done a graphical interface that lets you set up very easily the different parameters. And maybe I might try, and I've never done this, but since this product is aiming to to be interesting for research purposes. I will also create a MATLAB API, so people will be able to interface this module with MATLAB. So I think it sums up where I am right now with this project. Hopefully in 2 weeks, I should be able to receive the different board, and we'll see how to play with them. Okay, I think that's all for today. Thank you for following, and I will say bye bye.